Hello, everyone around the world. Welcome to this next webinar of the International Solar Alliance Experts Training Course. This is David Jacobs speaking here from Berlin. Today we will have session 33, which is dealing with the water energy nexus using solar PV in a water-constrained world. As you probably already know, this webinar series is organized in cooperation between the International Solar Alliance and the Clean Energy Solution Center. They are providing this very important platform for experts of solar PV and those who want to become experts in order to learn about the different aspects of this very specific technology. I am David Jacobs, founder and director of the consulting firm IET International Energy Transition. Been working in renewable energy policy design for the last 14 years, working in many countries around the world with policymakers from more than 40 countries around the globe. And in the last couple of years, there was more and more requests, not only from policymakers coming from very arid regions such as the MENA regions, but actually from policymakers all over the world to learn more about the opportunities of reducing water consumption within power sectors. And therefore this topic of solar PV and the reduced need of water in comparison with other technologies is becoming increasingly important. This training course actually consists of a total of 8 modules. We have 2 modules dealing with policies for distributed solar PV and large-scale solar PV. Another one dealing with the future of solar policies, where we try to look at how solar policies could potentially evolve in the near-term future, with solar PV now being the least cost power generation technologies, being also increasingly competitive on wholesale electricity market. What does this actually mean for market design and for support mechanisms? We also have 2 modules on technical integration and market integration. And this webinar is actually part of module 6, which deals with socioeconomic aspects of solar PV deployment, such as job creation, and in this case, water consumption and the potential reduction of water consumption within the electricity sector. And of course, we also have some webinars on off-grid solar, and last but not least, module 8 on the use of solar, concentrated solar PV in the heating and cooling sector. So this is more or less a standalone webinar. There's not really any other webinar of this webinar series which is directly related to water scarcity. However, if you have an additional hour, please feel free to also check out webinar number 37, dealing with ecosystem thinking, people, money, technology, and policy, which will certainly be a good addition to the topics that we're discussing here within the next hour. So here is what we want to cover. First of all, we start with a definition of the learning objectives of this webinar. Then we want to develop a better understanding of the water consumption that is related to the use of solar PV, also in comparison to the use of water from other power generation technologies, and what implications it actually has for power sectors and power sector planning in a water constrained world. And we will then close the webinar, first of all, with an outlook towards the more complex issue of water, energy, food nexus. And as with every webinar, we will also have a quite comprehensive further reading list, which will allow you to spend a couple of days or even weeks reading on this topic. And if this is too much for you, we also have the option of just giving you a few multiple choice questions, which allow you to check whether you've understood the major lessons learned from this webinar at the very end. So let's start with the learning objective. We want to understand, first of all, the implications of the climate crisis on water scarcity, because we're living in a more and more water constrained world, and we really need to face this and adapt our water management systems and also our electricity planning systems to this new emerging reality. Then we need to understand the water consumption of different power generation technologies in comparison. So comparing the water that is needed for solar PV and wind energy, for instance, with concentrated solar power, but also with fossil fuel-based power generation, such as coal and gas and nuclear. And of course, we also want to take a more in-depth looks into the water consumption of solar PV. When is solar PV actually requiring water? Is it more during the construction or the manufacturing of the solar PV systems? Is it more during the operation and maintenance, for instance, when cleaning the modules? So we will have a more in-depth analysis on this. And then last but not least, of course, we also want to understand the implications of lower water consumptions for the electricity sector. So we also have quite a lot of mini case studies peppered into this webinar. So let's first take a look at the emerging ongoing climate crisis and the implications for water scarcity. Yes, we live on a beautiful blue planet, which primarily consists of water. Surface of this planet is covered with more than 70% of water. However, of all of this water, only 2.5% is fresh water, and the remaining 97.5% is actually salt water. So we should really try to make the most efficient use and the best use of this very little fraction, which is actually fresh water, if we want to avoid desalinating more and more seawater, which is of course already happening in quite a lot of countries around the world. But we will always have to keep in mind that this of course requires quite a lot of energy, which once again needs to be produced, hopefully with renewable energy sources, but in many countries are currently with fossil fuels. So that doesn't really help us to mitigate climate change. It rather increases this vicious circle. Also important background information is the role of the agricultural sector. Currently and also historically, the agricultural sector is responsible for the largest part of freshwater use, currently about 70% of it. And it is also important to understand that we are not talking about any future scenarios. Here's an analysis done by the FAO, which has concluded that by 2025, around 1.8 billion people will be living in countries or regions with absolute water scarcity, so really heavily impacting their livelihood as well, and that up to 2/3 of the world's populations will actually be living under water stress conditions, so that water management will become part of their daily life very soon. So this is not just a fringe topic, this is actually a topic that will affect most of human beings on this planet. And this is why I'm really grateful to be able to provide also one session on this as part of this webinar series. So what will happen is, of course, an increase of drylands worldwide. We see desert and semi-arid areas growing steadily, not only in Asia and Africa, but also in Australia, in Europe, and in North and South America, which of course has huge implications for the people living in these areas. And we need to understand that water scarcity will only intensify with the emerging climate crisis. We have melting glaciers and changes in snowmelt regimes. We have increased evaporation from remaining freshwater reservoirs and water bodies and wetlands. Of course, we also have increased variability in precipitation with more extreme weather events, which has severe implications, of course, for the agricultural sector. We also will see more frequent floods affecting human settlements and croplands, but this sea level rise will not only affect the people that live next to it, but it will also affect the remaining freshwater reservoirs. And with saltwater intrusion, we will have increasing demand for irrigation and water in order to feed the growing population on this planet, and so on and so on. So this is a really complex issue, and it is very important to understand the implications of climate change, that the climate crisis, as many people now call it, will actually have severe implications on the availability of water. And the World Bank was wise enough to also quantify this economically, concluding that in many parts of the world, increasing water scarcity might actually significantly reduce the gross domestic product of these countries by up to 6%. However, they also argue that water scarcity will also spur migration and potentially spark conflicts within these regions, which once again highlights the needs of sophisticated and sustainable water management systems, not only in the electricity sector, not only in the energy sector, but of course, from a more encompassing point of view. And last but not least, what is very important to understand is that we have a combining effect of growing populations, of rising incomes, of an increasing middle class, of expanding cities, which are also consuming a lot of water, and that these combined effects really have increasing or even exponential water consumptions as one of their results. There has been some studies showing, for instance, that for each doubling of the gross domestic product, we don't only see a doubling of water consumptions, but we actually see a fourfold increase of water consumptions, once again showing that the water consumption actually operates exponentially to economic growth, which of course is not a trend which can continue for much longer, because due to climate change and increasing population on this planet, we will all, of course, need to deal with our remaining fresh water resources much more carefully. What is sometimes overlooked is also the implications of climate change, of the climate crisis on water temperature. Of course, many people talk about rising sea levels, and this is, of course, interlinked to increasing water temperature, which makes water expand and thus also increases sea levels. However, it also has significant implications for the power sector, because we're frequently using water resources, water flows, in order to cool our conventional power plants or our renewable energy power plants, in the case of concentrated solar power, for instance. And if then these rivers and other sources of water get warmer, then of course using them for cooling purposes will become more and more difficult. So we will not only see an increase of the temperature of waters in many parts of the world, we will also see a decrease in annual stream flows in many parts of the world. And the river temperatures are already increasing next to climate change due to urbanization and higher air temperatures, which are a result of this. And on top of this, we then have to combine all of this and understand that, well, if we have less water running in a river, and at the same time we have higher air temperatures, of course it is much quicker to heat up this remaining less water with higher air temperatures than it would have been if we would have had the river running at full speed with a full amount of water. So these are all feedback loops or vicious cycles, depending on how you want to term them. And we have to keep them in mind once we discuss the use of water for the energy sector or for the electricity sector in particular. Before we take a look at the water consumption from different power generation technologies, it is very important to differentiate two different aspects. And this is water withdrawal and water consumption. Water withdrawal means that you take a certain amount of water abstraction for a certain economic activity. It is sometimes also referred to as gross water abstraction or withdrawal. And just to give you an example, for instance, you have a coal-fired power plant which is standing next to a river, and you're using the water of the river in order to cool your coal-fired power plant. Then you're withdrawing this water, you're letting it run through your coal-fired power plant, but then it comes out at the end of a coal-fired power plant and re-enters the river, but with a higher temperature. But nonetheless, it is withdrawn, but then given back to the system. So this is a major difference to water consumption, because water consumption is a portion of water withdrawal that is not returned to the original water source after being withdrawn. So water consumption occurs when water flows to the atmosphere, for instance, through evaporation, or is incorporated in any products or plants. So as the previous example showed, there's of course some water withdrawn by the coal-fired power plants, but some water is also consumed, because in the process of cooling, some of the water evaporates, goes into the atmosphere, and is then factually lost and thus consumed. Or you could say, well, if I have a coal-fired power plant or a solar PV module, I need to fabricate them in the very first place. And in this fabrication process, for instance, for producing the glass for my solar PV systems, I need water, and this water is then built into the final product, the solar PV module. And this would then also mean water consumption. So it's very important to differentiate both of these terminologies, because we will see now a number of graphical illustrations, a number of comparisons in case studies where both of these aspects, water withdrawal and water consumptions, need to be clearly differentiated. Otherwise, we might get confused. So looking at it from a global perspective, here are some figures from one of the latest World Energy Outlooks of the International Energy Agency. You can see that global energy-related water withdrawal, so it's not consumption but withdrawal, ranges between 400 and 580 billion cubic meters per year. This is around 10% of total water withdrawal or water abstraction that is that we have in total worldwide. Here, then you can see the water withdrawal from different conventional power generation technologies, ranging from conventional gas, which has relatively little water consumption, all the way down to the more renewable energy-based primary carriers of energy, such as palm oil diesel, soybean diesel, sugarcane, ethanol. So in these graphs, you actually always see both once the water withdrawal and the water consumptions of these different primary fuels. So this is one very important lesson already, that the extraction of the fuels has of course very significant implications for water use and water withdrawal, as you can already see from this simple graph from the World Energy Outlook, showing you that yes, water consumption in the energy sector will grow, and it will primarily grow due to primary energy extraction and production, and not so much due to the use of water in power generation in particular. So therefore, I have highlighted this graph from the International Energy Agency from 2012. Now, before we start looking at water consumption in the electricity sector in particular, we first of all have to become familiarized with some of the different cooling technologies. Because over the last 50, 60, 70 years, we saw different cooling technologies being applied for conventional power technologies such as coal and gas and nuclear, but also for some of the renewable energy technologies such as concentrated solar power. So until the 1970s, most of the power plants were built with one-through or open loop cooling. That means that the water runs through the system's heat exchanger to condense the low pressure steam at the exhaust of the turbine. So this technology has very low water consumption, but it has quite a high degree of water extraction, of water withdrawal. And this, of course, makes these power plants very vulnerable to the risk of droughts or of high temperature events or competition for water resources, because once again, the example of my coal-fired power plant next to the river, if the river gets too warm or if there is a drought and there's not enough water running through this river, or if the agricultural sector also wants to use the water of this river, then I have a problem of continuing operation of my coal-fired power plant. This is also the reason why most power plants built after the 1970s have used closed loop or wet cooling, where the cooling water circulates between the condenser and the cooling tower, and therefore you have a lot less of water requirements, so a lot less water extraction, but you're actually consuming more water because in this circulation process between the condenser and the cooling tower, of course, this water evaporates, is being lost, and therefore the consumption level is higher. Nonetheless, you're no longer so much exposed to the risk of water running or not running through your one-through open loop cooling cycles. And then last but not least, in the last couple of decades, we saw more and more power plants actually being equipped with dry cooling, and these technologies actually function very similar to those of closed loop wet cooling. However, the water is simply replaced by air, which is of course very beneficial when you look at water withdrawal and water consumption. Both of them are practically eliminated. However, what happens, of course, is that air is not such a good medium for cooling as water is, and therefore also the efficiency of your power plant gets reduced quite considerably. And what also happens is that the capital cost of such systems are also significantly more expensive, 10 times more expensive than, for instance, open loop systems which have been used previously. So with this terminology and these cooling technologies in mind, we can now have our first look at the life cycle water withdrawal and also at the life cycle water consumption of different power generation technologies. For instance, when we look at the life cycle water consumption, you see here the renewable energy technologies, wind and solar PV at the very top of the graph with relatively low water consumptions. And then you see that in the case of concentrated solar PV, nuclear, but also the coal-fired power generation technologies, the water withdrawal and water consumption varies quite significantly and is also significantly higher than those of variable renewable energy technologies such as wind and solar PV. And also indicated in this graph, you of course see what happens when you move from one cooling technology to the other technology, cooling technology. So dry cooling being indicated here, or in the case of coal-fired power plants, natural gas-fired power plants, indicated here. So once again, showing you that by changing the cooling technology also within the conventional power sector, you can dramatically reduce water consumption. What is not shown in the graphs before is actually the level of water withdrawal in once-through cooling technologies, because they simply do not fit on the graph. This is why I have also added this graph from a study from Annual from 2017, where once again, they looked at the water withdrawal from different power generation technologies and from different cooling technologies. And you can see here quite clearly that the water withdrawals here indicated in gallons per megawatt hour in once-through cooling technologies can be up to 100 times higher than those of alternative cooling technologies or those of renewable energy power generation technologies. So once again, to keep in mind that this once-through cooling technologies really has a very much higher level of water withdrawal than the other power generation technologies and than the other cooling systems that we have in place. This is very important background information when we now start looking at some of the case studies of using water within the fossil fuel industry. So let's start with a look at the European Union, which is a rather special example because we still have a lot of power generation technologies within the European system that have been constructed before the 1970s. And as already indicated earlier, most of them are still using the old cooling technologies, which of course also leads to a situation where a lot of water is actually withdrawn for the energy sector. So this is an analysis by the European Wind Energy Association based on the European Environmental Agency, showing that water withdrawal from the energy sector actually accounts for 44% of total water that is withdrawn within Europe, increasing or being much higher than those of the agricultural sector, industrial sector, or also the public water supply. And this study has then suggested that the water used, withdrawn by the energy sector is actually equivalent than the use of 82 million households. That is more or less the population of Germany. We also have some interesting case studies from the US and from Germany concerning energy security and water consumption in the electricity sector. There was an interesting study by Annual, once again, analyzing in the United States what the impact was of water scarcity on running certain types of power plants. This is actually a phenomena that we see quite frequently in Europe, that we have curtailment of nuclear power plants, but also of coal power plants during warm summers, because they can no longer use the water that is available in the rivers, because they're based on once-through technologies. And if the water temperature within the rivers exceeds a certain threshold, then these power plants actually have to reduce output or stop operating altogether. So for instance, during one of the earlier heat waves in this century in 2006, when many thermal generators were actually first forced to curtail or shut down, we also saw that the spot market electricity price in Europe went up by 11%. So it has some financial implications. But of course, depending on how many of the power plants are really affected by this, it might also have some implications for security of supply. The analysis in the United States actually showed that between 2000 and 2015, there were more than 40 incidents of water-related curtailment, 18 of them related to coal-fired power plants and 25 involving nuclear power plants. Once again, And the researchers have identified 4 different categories why these power plants had to be curtailed or why they had to be shut down. And once again, it was primarily due to the fact that they were using one-through cooling technologies. So either the intake of the water was too warm, so the river that was cooling, that was supposed to cool my power plant, was carrying water that was too warm. What is also sometimes a problem is that if you already have a warm river, you are not allowed, due to environmental regulation, to warm it up further, because this might have very severe implications for the fishes and the natural habitat within these rivers. So this might also be a block and a reason why you would need to curtail. Sometimes both of this happens at the same time, or sometimes there were even instances where there was not enough water within the water bodies that were supposed to do the cooling, and therefore the coal or nuclear power plants needed to be stopped. And what is also then interesting is that the average available capacities of thermal power plants in the US and in Europe could potentially decrease by 4 to 16% in the summer months, meaning, once again, that if you assume that a lot of the capacity is actually required in order to meet demand, if you have this relatively substantial decreases of available capacity, this might actually also get you into trouble when it comes to energy security, security of supply altogether. And this is also the reason why most jurisdictions around the world are now shifting towards other cooling technologies, even though they reduce the efficiency of the power plant. From a security of supplies perspective, this certainly has a lot of advantages. This being said, let's now look at a country which has installed most of the conventional power plants later than in the United States and in Europe. So in South Africa, we see, for instance, that the industry or that the power sector is only responsible for 6% of water withdrawal, whereas the agricultural sector actually accounts for 63%, and then the domestic sector accounts for 31%. And this is, of course, due to the fact as well that South Africa has already implemented relatively early more advanced cooling technologies for the existing fossil fuel-based power plants, primarily coal-based power plants. And what is also important to know is that by regulation, the power sector has priority access to the water. They are a priority user. So in case there is water scarcity, then Eskom, the national utility of South Africa, would have first access to this remaining sources. This apparently has never happened yet, that there was such an extreme case of water scarcity, and it is still not clear what would really happen politically and socially if there would be a competition of water either for the food provision or for energy. However, at least from a regulatory perspective, the power sector is defined as a priority user of the water resources due to its very important strategic position. So, as already mentioned before, most of the coal-fired power plants which were constructed in the late 1970s, 1980s, 1990s were already using recirculating cooling technologies. And as you can see from this graph, in the 1990s and then 2000s, most of them were then also shifting either to dry cooling technologies. And this, of course, reduces the water consumption of the coal sector in South Africa quite considerably. What is, however, very important to understand when looking at the South African power sector is that in the last couple of years, there were some severe disruptions in the power sector. Not enough generation capacity was available in order to meet demand. And therefore, some of the old coal-fired power plants, which were actually already decommissioned, had to be returned to service. These are the RTS plants, which are indicated in red in the graph below. So they had to return to service in order to provide peak electricity demand during certain hours of the day. And these very old coal-fired power plants, first of all, had very high water consumptions due to their old cooling technologies, and they were frequently also located in water-constrained areas, which of course only made things worse. So therefore, from a South African perspective, it is very important to procure more renewable energy in the next procurement rounds. Therefore, to meet electricity demand with low carbon technologies and with respect to water consumption, to kick out all of these RTS power plants, which are actually using just as much water as the baseload coal-fired power plants in the country. And therefore, this would dramatically reduce water consumption within the South African power sector in the next couple of years. Let's also take a quick look at China. 79% of water withdrawal in China for all purposes occurs in water-stressed regions. We have a lot of regions, especially in northern China, close to the border with Mongolia, which already face severe water stress. Coal-fired power plants are responsible for around 90% of total water withdrawal in the power sector. And as you probably already know, China is also planning quite a big carbon capture and storage program, which could increase the total water requirements significantly because you need to have additional cooling capacity for the carbon capture process. As you can see here from this graph as well, you see the very high water stress levels, the very arid areas of China, primarily in the north. And in this analysis done by the International Energy Agency as part of the World Energy Outlook 2015, you can see that fortunately most of the new planned or new built coal-fired power plants in this area are now equipped with more expensive dry cooling, and that also a lot of retrofitting of existing wet tower systems is required in the northern part as part of the national water management system. And of course, what happens once you do this refurbishment is that, first of all, you increase the cost by adding this more expensive cooling systems. You also increase the network costs because you're installing coal-fired power plants in areas which are relatively far away from the load, but at the same time, the analysis from the IEA also showed that you are saving some money on coal transport because you're actually now constructing coal-fired power plants no longer in areas where you have available water cooling, but you're actually constructing them very close to the extraction place. Since you're using dry cooling, the water is not of your concern anymore anyway, and therefore you also have some benefits from a system perspective. Now, after having looked at some examples of coal-fired or fossil fuel-based driven water consumption within power sectors around the world, let's take a closer look at the water consumption related to solar PV in particular. So once again, here our introductory graph showing the comparison of the different power generation technologies. We now know that, yes, the water consumption of variable renewables, especially wind and solar PV, is significantly lower than those of other conventional power generation technologies, also much lower than those of biomass, biogas, concentrated solar power, and geothermal. But we really want to understand now what this blue graph represents and in which part along the value chain of a solar PV system water consumption actually occurs. There's an interesting study which was looking at the water consumption, life cycle water withdrawal from solar PV, here in the case of cadmium telluride modules, but it's relatively the same for all module types. So this graph indicates quite nicely that actually 50% of water required over a life cycle is related to the module manufacturing. So the electricity that is required for the module manufacturing, the glass, and so on. Then you have about 30% of the total water that is required for the balance of system. So for instance, the frames that the modules are placed on, and then building the whole foundation of the solar PV systems, the inverters as well, the copper that is needed, the steel that is required, and so on. So this is 30%. And then we have about 12% only of the water that is required during operation and maintenance, and that is cleaning of the solar PV modules. Now, there's frequently a misconception that solar PV systems always have to be cleaned by a lot of water, and that this would cause, of course, a lot of problems in water scarce, arid areas around the world where you see actually a lot of the solar PV deployment happening. Here is one of the images that suggests that yes, you will definitely need a lot of water if you're just using a hose and cleaning it from bottom to top as if you would have infinite amount of water. However, I just wanted to highlight in the next couple of minutes that there's a lot of different technologies now available for cleaning solar PV modules, and many of them are actually no longer using any water. So you have wet cleaning technologies, you have dry cleaning technologies, you then of course also have manual cleaning technologies, track mounted, as you can see in the right top corner in the picture, semi-automatic cleaning, fully automatic cleaning, as you can see in the bottom, fully automated system, which is fixed, installed to the solar PV panels and which just runs its cleaning cycles whenever it is required. And then, of course, we also have quite a lot of research on robots and drones, which might be able to do the cleaning of solar PV panels in a fully automated way and hopefully also cheaper way in the near-term future. So this is just to give you an overview of the wide range of cleaning options that are available for solar PV modules. And as part of dry cleaning, there has also been some interesting research done on what kind of technologies work, which work not so fine. So a lot of the dry cleaning actually works with mechanical brushes, sometimes in combination with vacuum cleaners or maybe microfiber-based cloth wipers, as you can see here in this picture, also sometimes combined with vacuum cleaners. So next to these mechanical cleaning options, you also have some research going on related to chemical self-cleaning. Quite a lot of companies are currently testing nanofilms on solar PV modules, which on the one side can reduce the output of the solar PV systems, but on the other hand, can keep away quite some dirt and dust from the solar PV system. And this would then again increase the performance of the solar PV module. So this just to give you an idea of the different cleaning options. And of course, the selections of these cleaning options really depends on a lot of factors. So first of all, it depends, of course, on the water availability or water scarcity in your regions. When you have your solar PV system installed in a very arid area, it does not only make economic sense to use dry cleaning technologies, but it also probably makes sense from a regulatory point of view, because probably the environmental regulation, for instance, in northern China, does not really allow you to use any water to clear your solar PV panels, and therefore you are looking into dry cleaning options by default. And then, of course, what also impacts the selection of your cleaning options for solar PV modules is expected soiling levels. Do you have a lot of pollution in the air, maybe due to sandstorms in the regions, or maybe because you're very close to urban centers or to cities where you have a lot of pollution in the air, which then settles on your solar PV system forever. This, of course, also determines the frequency of cleaning. Do you need to clean them once a year? Or do you maybe need to clean them more often? And then, of course, you're interested in more automated processes. Of course, the type of PV plant also affects the choice of the cleaning option. The space, for instance, between the single rows of the solar PV plant has to be broad enough for tractor paths. If they are narrower, less than 3 meters, then you need to probably come up with alternative cleaning options. And last but not least, also the proximity to label sources are very relevant for your choice, because if you have a solar PV system in a very remote area where cleaners cannot come in order to do the job manually, then of course, once again, you're probably more interested in semi-automated or fully automated cleaning options. So this is just a quick overview of the different cleaning options for solar PV. Even though cleaning water that is used for cleaning only uses about 12% of the total water that is used for solar PV system on a life cycle perspective, yet in very arid areas, this is of course very important. So last but not least, let's look at some case studies that show to what extent solar PV and renewable energy technologies and also advanced cooling technologies for fossil fuel-based power plants can actually reduce water consumption in power sectors, in energy sectors altogether. Maybe let's start with a case study from India, where Irina did an interesting analysis concluding that the combination of improved cooling technologies for the coal-fired power plants with renewable energy deployment, primarily wind and solar PV, could reduce the freshwater consumption in India, in the Indian power sector considerably, namely by up to 84%. The intensity of water withdrawal can be reduced in India by moving to a more renewable energy heavy and more dry cooling heavy power sector. Similar results have also been shown in some US studies. Water withdrawal currently is still very heavily dominated by through cooling demand of coal and nuclear power plants. However, if you switch to dry cooling or other cooling, and if you switch to a power sector which is then dominated by solar PV, you can actually reduce the water withdrawal from currently 42 trillion gallons down to 8 trillion gallons per year in the year 2050. And interestingly, here you can see also the impact on different regions. For instance, you can see here quite a significant effect on the very arid areas that you have in Southern California, that in some of these regions, in 4 regions, water withdrawal is actually reduced by more than 90%, and even in the more central plains of the United States, you still see significant reduction in water consumptions in a power system which is dominated by solar PV. So very promising also for this country that moving towards renewables and solar PV can actually reduce water consumption quite considerably. And of course, the same is true also for the Saudi Arabia and neighboring countries. All of these countries have established renewable energy deployment plans. And here again, Irina did an interesting analysis to see if they reach these targets, which they have defined until 2020, 2030, 2032, what would this actually mean in terms of reduction in water withdrawal. And here, for instance, you can see if Saudi Arabia goes all the way through with a plan of installing 54 gigawatt of renewables by 2032, that would actually reduce water withdrawal within the country, which certainly has the problem with available fresh water. It would reduce it by more than 25%, 28%. So, cutting a long story short, here again, a summary of what we have hopefully learned in the last hour. So we have an ongoing climate crisis, which will further increase water scarcity. By 2025, we will have most of the people around the world living under water stress conditions, and up to 2 billion people living in countries and regions with absolute water scarcity. The energy sector is responsible for about 10% of water use globally, and in the electricity sector, coal-powered power plants play a very crucial role in water consumptions. And we also learned about the different cooling technologies which are available to already start mitigating these problems. However, by moving towards decarbonized power systems primarily based on solar PV and wind energy, water consumptions in power sectors can be further reduced, and thereby power sector can become a very important contribution to sustainable water management systems within your country. As mentioned at the very start of this webinar, we also want to take a short look at the more complex issue of the water energy food nexus. So what we've done really in the last hour was really just to look at the water needs in the power sector, the water requirement for solar PV, for fossil fuel-based technologies. However, you could of course spend an additional hour also looking at the energy needs of the water sector, that you see what type of energy is actually needed in order to pump water up or to transport water to the consumption levels, and so on and so on. So this would already make it significantly more complex. And then if you add the third component, the food provision, food security to this picture, then of course it becomes even more complex. You need to take the water that is needed for growing food into consideration. You also need to take the energy that is needed for crops and irrigation into consideration. You have to look at the agricultural land that is needed to grow crops such as biofuels. So you need to establish a really holistic view on understanding and hopefully managing this energy water food nexus well. So there is some very interesting reports on this in our extended reading lists. There are important reports from the Joint Research Center of the European Union, for instance, here from 2019, which you look at the energy nexus in Europe. We also have an interesting study from IRENA from 2015 looking at the renewable energies and in the water, energy and food nexus. Important reports from IEA, European Wind Energy Association, annual. All of those were mentioned in this presentation. And last but not least, I really liked as well the FAO documents where they had very nice graphical illustrations on soil, land, and water use. So enjoy reading those if you have the time. Thank you once again for the International Solar Alliance and the Clean Energy Solution Center for providing this very important platform. Please also check out the more than 40 other webinars in this webinar series. And as always, we're closing with some simple multiple choice questions for you. I hope you have enjoyed this webinar. I hope you have some ideas for further research and further investigations. Feel free to contact us if you have further questions. And thank you very much for listening. Talk to you soon. Hear you soon.